Now we have to try and build a bilbo. We will try a 4-bit bilbo. So, a 4-bit bilbo will have 4 flip flops. And the D input will, let us say, come from a 4 to 1 mux. So, there are 4 inputs. And let us look at the first mode. The first mode is parallel in, parallel out. Let us say the control lines are here, C0 and C1, and they will be connected everywhere. So, if it is 0 0, we have to take the parallel input and connect. So, let us keep the parallel inputs here. Let us say we call it P0, P1, P2, P3. And let us call this as Q0, Q1, Q2 and Q3. In the next one, let us say we are just doing as a shift register. So, serial in will come here and the output of Q0 will go here, the output of this flip flop will go here, the output of this flip flop will go here, and this output is also available to you as serial out. In the third one, let us say we want it as a PRPG. So, we will do this as a Galva LFSR. Okay. So, the Galva LFSR is 1 plus x power 3 plus x power 4. So, this is a polynomial for 4-bit LFSR. I think both of these will work. 1 plus x power 4 will also work, and 1 plus x cube plus x power 4 will also work. So, we need an XOR gate between the third and the fourth. Okay. So, there has to be, if I am using this one, there has to be 3 flip flops ahead of us. So, 1, 2 and 3, and this is where we are going to put an XOR gate. And the input to that LFSR will come from the output of this guy and the input of this guy, and this should go as the multiplexer input. And then this guy will come from this Q3, and this guy will come from here. Okay. When we do it in circuit verse, you will get a more clear picture. In the last one, we are doing as an MISR. Okay. So, 0 0 means it is parallel in, parallel out. 0 1 means shift register. 1 0 means LFSR or PRPG, and 1 1 means MISR. So, in the MISR, we will take the parallel input that is coming in and XOR it with this guy. and that will be connected here. Similarly, parallel input coming from here and these two guys and connect it here. Parallel in P2 and this guy. Then goes here. It's a little clumsy here, but we will draw a better diagram. Say P3 and this guy. This has to come here. So, first let us create a D flip flop, and we will also create a multiplexer. We will need a 4 to 1 mux. Sorry. Okay, so 4 to 1 mux. And this will go here, and we need to connect the enable to logic high. Okay, we will connect the preset to 0. Okay, and then reset will be connected here. Okay, clock will be connected here. And we will have 4 inputs, one for 0 0, then so this input we will call it as 0 0. This input we will call it as 0 1. Then this input is 0 1 0. And this input we will call it as 1 1. Okay. This input is called reset. And this input is the clock. Okay. And we will need one output, which is the Q output. You could have called this D00, that would have been more, it's okay. That is more illustrative, D00 be data 00. row called D00, D01, D10, then D11. Okay, and the last one is Q. This is a Q output. So we have built a one building block. Okay, and now we can go to the next guy. Okay, and we will call it as Bilbo, and maybe this we should call it as we should give it a name. So instead of main, we will call it mux ff mux, mux ff is okay, mux ff. Okay. So in the Bilbo, we will need 4 of these muxes, mux ff. So we will say insert 4 of these guys. Okay. Resets have to be connected. And we will call this input as reset. This is a Bilbo reset. Okay. Similarly, the clocks will have to be connected. Let us create another input called clock. And these are connected. Okay. So we have connected the clocks. Now we have to connect these. In the mode 1, we will have 4 parallel inputs. So we will call these as maybe P0, right. So P0 goes to D00. Then P1 goes to D00 here. Then we should call this P1 by the way. Similarly, we will have P2. and we will have P3. So, D00 is connected to P D00 and this is P3 is connected to. And I think I forgot to bring the control inputs, right? So, go back here, the control inputs must be connected. So, there are two of these, okay. It does not look like that, but there are actually two. So, you will have to say bit width is 2. So, there are two of these, okay, and we can call this as CNTRL or CTRL or something. Okay, I forgot that. So, when you go here, the CTRL has been introduced here. All the CTRLs will have to connect it together. And there is a 2-bit input here. This input should be 2 bits. Okay. So, if it is 0 0, then P0 should get loaded. Let us create 4 outputs also. Maybe we can put it right here. So, this is our Q0. And similarly, we have Q1 and we can call this Q1. Then we have Q2 and we have Q3. Okay. You can also tie some LEDs here just for visual feedback. It allows you to just put these LEDs . Right now all the LEDs are off because we have 0 0 0 0, that is because the reset is high. So, if you make reset 0 and let us say we bring 1 0 1 0 or 1 0 1 1 by toggling the clock. See, clock is right now 0. If I clock it 1, you will see that that 1 0 1 1 got latched here. Okay. So, it is correctly working as a parallel in parallel out. The first mode we have verified. Okay. In the second mode, it has to act as a shift register. So, we will bring in a shift input and connect it to this guy here. So, this is my shift input or serial in. okay, and this is also serial out. So, Q2 is also serial out. If you want, we can bring another output, but there is no need. Then the output of Q should go as serial in for this. So, this should also go as serial in for this. This should go as serial in here, and this should go as serial in here. Okay. Now, let us see. Let us make this 0 1, and serial in is 1. So, if you start shifting, right, it should shift these ones through this. Okay, let us see. See, this 1 got shifted here. Then one more clock, one more clock, one more clock. Now, if I make this 0 and clock, see this 0 got shifted, another 0, another 0, another 0. So, we have verified the second mode, that is, it acts as a shift register correctly. In the third mode, it has to act as a LFSR, and we are looking at the Galva LFSR. So, the XOR gate will have to be here. Okay, so, let us put an XOR gate here. And that XOR gate will take as inputs these two guys, the output of this and this input. Right. And that should go into D10. And this guy has to come back and go as D10 here. This D10 is same as this guy. This is just a shift guy. Okay. Now, let us verify the 10 mode. We can start with maybe right now it is all in 0000 state. So, we should not have 0000. So, first let us make it in 01 state or 00 state and load the 0001 is a seed. Okay. So, now reset is 0, let us lower the clock. Okay. So, now it is in the 0001 state. Okay. So, now we go to the 10 state and we will keep clocking, right. Let us see what happens. So, if I clock it, it went to 1001 state, that is 9. Then one more clock, something is wrong, something is wrong. Let us verify that is all correct. So, we are sending this over here. This we forgot, right? We forgot. Okay. So, let us go back to reset. So, we load 0001 by loading 00, lower reset and increase the clock. So, we are back in the 0001 state. Now, go back to 10 and start clocking. Clock is 0, then clock triggers. So, we got to 1001 state, then that was 9, then we got to 1101, that is 13, then 15, then 14, then 7, then 10, then 5, 11, 12, 6, 3, 8, 4, 2, then back to 1. So, it cycled through, I believe, all the states, 15 states. Okay. So, it is working correctly as the LFSR. In the last one, where it has to act as an MISR, right, we will have to put XOR gates everywhere, and we have to take the parallel in coming from the circuit and the test, and this feedback coming from here, and this should go as D11. Okay. The same thing here, another XOR gate, and this feedback line should go here, and the parallel input should go here, and that should go to D11. And then one more XOR gate, this feedback line has to go here, and then this parallel input has to go to the other input. And then this goes here. Okay. And one more XOR gate here. Again, this feedback guy goes here, and this P3 has to go here. And this output has to go to D1. Oops, sorry. Okay. So, we have connected everything, I believe, correctly. So, let us verify that it acts as an MISR. How do I do that? I will start by reset. So, all flip flops have 0 0 0 0, then go to 1 1 mode. So, pretend that there is a circuit and a test which is sending data. So, let us assume that the first data is 0 0 0 1, then we will clock it, lower the reset and clock it. So, it goes to the 0 0 0 1 state. If the same data is presented again, it goes to some other state. Maybe another time the same data is presented. So, it goes to these two states, At some stage the data will change, maybe it will go to 1 1 and then it will go to this state. Okay. And if there is a fault, the signature will be different. Okay. Right now we simulated it as an MISR. So, this is a Bilbo. Okay. So, if I now take let me call this guy as CNTRL. Now, you can insert test circuit. Now, I can insert a Bilbo. The Bilbo has 4 inputs, 4 outputs, 2 control signals and 1 serial in. If you want, we can also have the serial out if it is of any value to you, but it is the same as Q3. I think we forgot to label this as Q3. Okay. So, this is Q3. So, I believe Q3 is same as serial out. So, we do not have to separately bring out one more. So, now if there is a circuit and a test, okay, maybe we will include maybe a decoder or something like that. And maybe it has 4 outputs. And we need an reset. This is the reset at the top level. Then we will need a clock. All right. Then the outputs of these will go as inputs to P0, P1, P2, P3, because we are planning to test this decoder. Yeah. See, these pieces of wire, we should be very careful. So, there is some wire there. Okay. So, this is the circuit and the test. And we are connecting. We connect P0, P1, P2. No. You have to be very careful. P2 and P3. Okay. Then there is a control signal for the Bilbo. So, we will create one 2 input control signal here. So, this is a 2-bit input. and we will connect it here. So, this is Bilbo configuration. You can call it config, and there is some input here for this decoder. See, this decoder is a trivial circuit that I am planning to test. Okay, there should be 2 bits. So, it is a 2-bit decoder producing 4 inputs, and that and then this Q0, Q1, Q2, Q3 we can connect as outputs. So, another output. So, right now reset is 1 and therefore, the circuit is showing 0 0 0 0. Let us put this in the signature register mode. So, that should be 1 1 I guess, right, and reset should go down to 0, right, and then let us we will change this from 0 0 0 1 etc., right. So, initially it is 0 0, let us clock it once. So, it went into this state. Now, we will change it to 0 1 and clock it again. Then we will change it to 1 0 and clock it again, okay. And last but not the least 1 1 and clock it again. Okay. So, this is how the MISR states are changing. Okay. Now, in this 1 1 let us do some more clocks. So, these are this is how I am doing the multiple input signature register. So, once again, so initially reset to 0, this is the MISR mode, and then I start with 0 0, okay, then change it to 0 1, then 1 0, then 1 1, and then we will assume that now in the 1 1 mode we will apply 4 more clock pulses. So, 1 2 3 4. So, this is the signature, the good circuit signature. Okay. Now, let us create the fault somewhere here. Okay. So, this input is, let us say, connected to ground or something like that. It has a stuck at fault. Once again reset, clock is 0, start with 0 0, and then reset 0 and clock. So, this state is 1 0 0 0, then I apply 0 1, then clock, then 1 0 clock, then 1 1 and clock, and then again 4 more clocks, 1 2 3 4. So, you can see that there is a difference. Earlier it had gone to the 0 0 0 1 state, but now it is going to 0 0 0 0 state. So, in a trivial way, it illustrates how the MISR works.